Sometimes, the greatest discoveries in science are not born from brilliant insight or meticulous observation, but from a profound, almost poetic mistake. They emerge not as facts unveiled, but as projections of our deepest desires, shaping reality to fit a powerful, pre-existing narrative. This is the paradoxical origin story of one of our solar system's most enigmatic worlds, a tale less about the cold mechanics of celestial bodies and more about the compelling, sometimes blinding, power of human expectation. The stage for this cosmic drama was set in the early 1900s, within the ambitious mind of an American businessman turned astronomer, Percival Lowell. Haunted by what he perceived as anomalies in the distant orbits of the ice giants, Uranus and Neptune, Lowell became consumed by the hunt for a hypothetical celestial body he christened Planet X. He believed this unseen behemoth, lurking in the cold, dark reaches of space, was gravitationally tugging at its colossal neighbors, causing minute yet detectable deviations from their predicted paths. His calculations, complex and intricate, were meticulously performed, yet they harbored a fatal flaw. They were founded upon observational data of the ice giants that, unbeknownst to him, contained subtle, deeply ingrained inaccuracies. This singular, incorrect idea, however, ignited a quest of almost mythological proportions across the global astronomical community. Lowell, a man of immense personal wealth and even greater conviction, poured his resources into this obsessive pursuit. At the Lowell Observatory, a state-of-the-art facility he himself founded in Flagstaff, Arizona, archives reveal the tangible evidence of this fixation: a purpose-built telescope, specifically designed and engineered for the solitary mission of scouring the night sky for this elusive gravitational giant. It was a testament to the power of a belief, however misguided, to drive monumental scientific endeavor. For years, the search continued, a grueling, painstaking task involving photographic plates that captured millions of star fields. Then, in 1930, a young, tenacious astronomer named Clyde Tombaugh, barely in his early 20s, made a pivotal observation. After patiently comparing thousands of photographic plates, he detected a tiny, faint speck of light that had shifted position against the unchanging backdrop of distant stars. This was it. The discovery was hailed as a monumental triumph of predictive science, the ultimate vindication of Lowell's long-sought ghost. The world celebrated, and the ninth planet was officially named Pluto, a nod to the Roman god of the underworld and, perhaps not coincidentally, to Percival Lowell's initials. Yet, there was a profound, almost cosmic irony lurking beneath this celebrated discovery. Pluto was not a gravitational behemoth, thousands of times the mass of Earth, as Lowell's calculations had so confidently predicted. It was, in fact, a tiny, faint speck, found largely by a stroke of serendipity, a mere coincidence that it happened to be near one of the predetermined search locations. It was a world so incredibly small that it possessed only a minuscule fraction of the gravitational pull needed to perturb the colossal orbits of Uranus and Neptune. To put its size into perspective, its actual mass would later be found to be less than 1/500th of Earth's, a mere whisper compared to the thunderous giant Lowell had envisioned. From its very inception, Pluto's status as a planet was not a pure scientific fact, but a cultural artifact. Its planethood was born from a powerful, irresistible narrative. The lone hero, Percival Lowell, whose brilliant prediction led to the discovery of a lost world, confirmed by the diligent work of a young apprentice, Clyde Tombaugh. This compelling story was so deeply ingrained, so emotionally resonant, that for decades the glaring discrepancy between the predicted giant and the tiny world actually found was largely overlooked, even dismissed by many in the scientific community. We find ourselves grappling with an institutional-scale manifestation of confirmation bias. The desire for Planet X to exist was so potent, so deeply embedded in the collective scientific consciousness, that the community, almost subconsciously, projected the properties of Lowell's predicted giant onto the newly found enigmatic object. Newspaper clippings from the 1930s vividly illustrate this initial misconception, proudly announcing the discovery of a large new planet to an eager public, firmly entrenching this initial, inaccurate perception in the public imagination. The initial mass estimates for Pluto were wildly inaccurate, a testament to this shared dream. Early calculations suggested a mass comparable to Earth, then steadily revised downwards to perhaps that of Mars, then Earth's moon, and ultimately even smaller. This progressive downward revision, spanning decades as observational techniques slowly improved, was akin to a slow, painful awakening from a prolonged, deeply cherished dream. This was no simple discovery. It was the genesis of a 75-year-long case of mistaken identity, driven by that spectral ghost in the machine of celestial mechanics. It was a grand, unfolding illusion that would, in time, set the stage for an inevitable scientific reckoning, one that would dramatically shake the very foundations of our solar system map. Pluto, as it turns out, was never truly the planet we thought it was. It was, in its essence, a placeholder for a human-made myth, a faint, barely perceptible smudge. It appeared not as a grand pronouncement, but as a subtle aberration on a photographic plate captured in 1978, a detail most might have dismissed as a minor defect. Yet this minute imperfection, a cosmic whisper from the distant reaches of our solar system, was about to unravel a 75-year-old illusion and fundamentally reshape our perception of a world we thought we knew. It was the first, almost imperceptible crack in Pluto's long-held planetary facade, the beginning of a scientific reckoning driven by one astronomer's meticulous gaze. The man behind this pivotal observation was James Christie, a dedicated astronomer working at the United States Naval Observatory. His task involved routine astrometric measurements of Pluto, comparing countless photographic images taken at different times. Day after day, he scrutinized the tiny pinprick of light that was Pluto, often a frustrating and repetitive task. However, on one particular set of plates, Christie noticed something peculiar. Pluto appeared subtly elongated, not perfectly round as it should have been. For anyone else, this might have been brushed off as an atmospheric distortion or a photographic flaw, a fleeting anomaly to be ignored. But Christie was different. His keen eye and rigorous scientific mind refused to let the anomaly pass. He suspected it was not an error of the telescope or the film, but something far more profound. His meticulous investigation, comparing this elongation across dozens of photographic images taken over several years, slowly revealed a consistent pattern. The bulge was not static. It appeared to shift its orientation around Pluto, hinting at something orbiting the distant world. What he had discovered through sheer persistence and scientific insight was not a defect, but a massive moon locked in a surprisingly tight, intimate dance with Pluto itself. He named this newfound companion Charon, after the ferryman of the dead in Greek mythology, a fitting name for a moon orbiting the celestial ruler of the underworld. The discovery of Charon was, in itself, a technological triumph, pushing the very limits of ground-based observation in the late 1970s. Telescopes of that era, even the most powerful ones, were reaching their absolute maximum resolution when trying to discern such a tiny, faint object billions of kilometers away. But the true significance of Charon lay not just in its existence, but in the profound laws of physics it suddenly unlocked. For the very first time, astronomers now had a binary system, two celestial bodies orbiting a common center of mass, allowing them to apply one of the most fundamental principles of orbital mechanics, Johannes Kepler's third law of planetary motion. By precisely measuring the orbital period of Charon around Pluto and the distance between them, astronomers could, with startling accuracy, calculate Pluto's true mass. The result, when it finally emerged from the complex calculations, was nothing short of a bombshell. Pluto was not merely small, it was minuscule. Its true mass was revealed to be less than 1/5 the mass of Earth's own moon, a staggering revelation that reshaped everything. To put that into perspective, if Earth's moon were a professional basketball, Pluto would be no larger than a tennis ball, and its gravitational pull would be commensurately tiny. This single, precise data point, derived from the faint, distant light of a newly discovered moon, acted as an astronomical telltale heart. It exposed with irrefutable clarity the long-held secret that Pluto was, in essence, an imposter planet. It was utterly, demonstrably incapable of causing the gravitational wobbles in Uranus and Neptune that had prompted the original search for Planet X nearly a century earlier. The entire rationale for Pluto's celebrated discovery in 1930 had been built on a phantom premise, a miscalculation stemming from inaccurate historical data of the ice giants. The ghost of Planet X, which had haunted astronomy for decades, was finally laid to rest by the indisputable evidence of its gravitational insignificance. This revelation from the Pluto-Charon system connects to a broader, fascinating pattern in the history of science. Time and again, the discovery of a companion object has revolutionized our understanding of the primary body. From the intricate dances of binary stars that allowed us to measure stellar masses, to the subtle wobbles of distant suns that reveal unseen exoplanetary systems, the presence of a celestial partner acts as a cosmic scale, a precise instrument for unlocking fundamental properties. Charon performed this exact function for Pluto, forcing astronomers to confront the reality that their supposed ninth planet was far from the massive world it was once believed to be. The discovery of Charon, therefore, marked Pluto's first, unofficial demotion. Its identity began to shift dramatically from that of a solitary, planet-like wanderer at the edge of the solar system to the dominant member of a strange new type of celestial couplet, the binary planet. No longer was it a lone sentinel. It was part of a tightly bound pair, its true nature revealed through the gravitational embrace of its companion. This was no longer a story of a planet and its moon in the familiar Earth-Moon sense, but rather a complex gravitational balancing act, a miniature solar system in its own right, offering a glimpse into a new, previously unimagined class of objects that would soon come to dominate our understanding of the outer reaches of the solar system. The subtle elongation on a photographic plate, the faint moon Charon whispering Pluto's true, tiny mass across billions of kilometers, those were the initial cracks in a 75-year-old illusion. But even as that quiet truth began to settle, a far more powerful force was gathering momentum, not in the distant reaches of the solar system, but here on Earth, in the laboratories and observatories of our world. It was a technological revolution, a fundamental shift in how we perceived the cosmos, and it was about to unleash a data tsunami so immense, so overwhelming, that the familiar, tidy 9-planet model of our solar system would be utterly drowned. For decades, astronomers had relied on photographic plates, glass sheets coated with light-sensitive chemicals, to capture the dim glow of distant stars and planets. This was an arduous, painstaking process, akin to trying to fill a swimming pool with a thimble, especially when searching for faint, moving objects against a crowded stellar backdrop. But in the 1990s, a seismic shift occurred. Laboratories and observatories across the globe began to widely adopt a new technology, charge-coupled devices, or CCDs. These were not just incremental improvements, they were electronic eyes, infinitely more sensitive and efficient than any photographic plate could ever be. Where a photographic plate might capture only a few % of incoming light, a modern CCD could convert up to 90% of those faint photons into digital information, making it vastly superior. This monumental leap in light-gathering capability and data processing meant astronomers could now scan the sky with unprecedented depth and speed, seeing objects that had remained hidden in the cosmic shadows for billions of years. Enter two meticulous and visionary astronomers, David Jewett and Jane Liu. Armed with these new digital tools, they embarked on systematic surveys, meticulously sweeping vast swathes of the night sky, searching for faint, slow-moving objects beyond Neptune. Their persistence paid off handsomely. In 1992, they announced the discovery of a small icy body, provisionally named 1992 QB1, or simply 92 QB1. This was not just another minor celestial find. It was the shot that started a revolution, echoing through the quiet corridors of astronomical institutions. 92 QB1 proved, unequivocally, that Pluto was not a lonely outpost, the solitary guardian of the solar system's icy frontier. Instead, it was merely the first sighted member of a vast, sprawling third zone of our solar system, a region we now know as the Kuiper Belt. This vast expanse, stretching far beyond Neptune's orbit, is home to billions of icy bodies, some perhaps as large as small planets, a cosmic reservoir of primordial material left over from the solar system's formation. The discovery of 92 QB1 opened the floodgates. What began as a trickle in the 1990s soon became a torrent in the early 2000s, a veritable cascade of new worlds emerging from the darkness. Astronomers began to assemble what one might call a rogues gallery of icy, distant bodies, each challenging our preconceptions about what lay beyond the gas giants. There was Quaoar, discovered in 2002, roughly half the size of Pluto. Then came Haumea in 2003, a peculiar, elongated object spinning so fast it looked like a cosmic football, and Makemake in 2005, another icy behemoth. Each new discovery was a data point, a stroke on the canvas that revealed a universe far richer and more populated than anyone had previously imagined. Leading this relentless hunt for these large, distant bodies was the American astronomer Mike Brown and his dedicated team at the Palomar Observatory. Their systematic survey was a masterclass in cosmic archaeology, designed specifically to unearth these hidden giants. Brown often described it as pushing the limits of what telescopes can do, spending countless nights meticulously sifting through terabytes of data, and in 2005, his efforts culminated in the discovery of the ultimate disruptor, Eris. This was not just another Kuiper Belt object. Eris was confirmed to be even more massive than Pluto itself, its size estimated to be around 2,326 kilometers in diameter, compared to Pluto's 2,376 kilometers, but with a 27% greater mass. This single data point did not cause the crisis in planetary classification, but it was its explosive culmination, the undeniable truth that shattered the existing, rather informal, scheme. This was a classic astronomical paradigm shift, a concept famously articulated by the historian of science, Thomas Kuhn. It was not unlike the data-driven revolution seen in other scientific fields. Consider genomics, where the sudden explosion of DNA sequencing data forced biologists to discard older, simpler models of inheritance and embrace the staggering complexity of genetic networks. Or particle physics, where a deluge of new subatomic particles from powerful colliders forced physicists to expand their standard model. In astronomy, the flood of new information from the Kuiper Belt forced scientists to confront a profound existential question. What, precisely, is a planet? The conversation was no longer a philosophical debate about Pluto's status. It was a stark, logical, and semantic crisis. The question was no longer simply, is Pluto a planet, but rather, if Pluto is a planet, then what about Eris with its greater mass, and Makemake, and Haumea, and dozens of other yet-to-be-named objects, some potentially even larger, lurking in the frigid outer reaches? Astronomers, for the first time in their history, were forced to confront a problem they had successfully avoided for decades: the absolute necessity of creating a scientifically rigorous, universally agreed-upon definition of the word planet. This task, as the coming years would reveal, would prove to be far more political, more emotional, and more contentious than anyone could have possibly anticipated. The old, comforting map of our solar system, with its 9 distinct worlds, was simply no longer fit for purpose. It was overwhelmed by the sheer, undeniable weight of new data. The year 2006, Prague. In the sweltering August heat, the venerable halls of the International Astronomical Union's General Assembly became an unexpected battleground. For decades, the definition of a planet had been a casual assumption, a cultural understanding handed down through generations. But the recent deluge of new discoveries in the outer solar system, objects like Eris challenging Pluto's very right to the planetary throne, had ignited a crisis. This wasn't just a scientific debate, it was a deeply human drama, a collision of egos, philosophies, and the very sociology of how science progresses. Step into the corridors of the Prague Congress Center, where the air hummed not just with the murmurs of thousands of astronomers, but with a palpable tension. Behind closed doors and in heated public forums, the reclassification of Pluto, and indeed the entire architecture of our solar system, was on the line. The initial proposal, crafted by an influential committee led by the renowned historian Owen Gingerich, aimed for a broad, inclusive definition. It was a big tent approach, rooted in a geophysical understanding of what makes a celestial body. This proposal championed the idea that any object orbiting a star, large enough to be rounded by its own gravity and not itself a star, should be considered a planet. If adopted, this would have seen the solar system swell to a planetary family of 12, welcoming not just Pluto and the newly discovered Eris, but even the asteroid Ceres, an object residing in the main asteroid belt between Mars and Jupiter. Initially, this expansive vision garnered significant support. It felt intuitive, accommodating the new discoveries without demoting a beloved world. Yet, as the debates raged on the convention floor, a fierce backlash erupted from a vocal faction, the dynamical astronomers. For them, a planet's intrinsic properties, its roundness or internal heat, were secondary. What truly mattered was its gravitational dominance over its orbital path. These scientists argued that a true planet must be the celestial king of its own neighborhood, clearing away or assimilating all other significant debris along its orbital highway. This was a fundamental clash of scientific cultures. Geophysicists, often planetary scientists who study the internal structure and surfaces of worlds, focused on what an object is. Dynamicists, those who meticulously track orbits and gravitational interactions, cared profoundly about an object's role within the intricate celestial mechanics of the solar system. The compromise forged in that crucible of debate was the final three-part definition that would forever alter our cosmic map. A planet must orbit the Sun. It must be massive enough to be nearly round, and critically, it must have cleared the neighborhood around its orbit. It was this third criterion that proved to be the most contentious and arguably the most problematic. Consider the implications. Earth, our own planetary home, shares its orbit with thousands of near-Earth asteroids, countless rocky remnants that it has not, in fact, entirely cleared. Jupiter, the colossal king of our solar system, coexists with the Trojan asteroids, two vast swarms of space rocks trapped in gravitational sweet spots along its path. Technically, by the very letter of this new definition, even these undisputed giants of our solar system could be seen to fail the cleared its neighborhood test. The ambiguity was immediate and deeply frustrating to many. The vote itself was an exercise in scientific sociology, a dramatic, last-minute affair that underscored its controversial nature. It took place on the final day of the conference, long after the initial buzz had subsided and the vast majority of attendees had already departed. Of the nearly 10,000 members of the International Astronomical Union, a mere 424 scientists cast a ballot. This was hardly a universal scientific consensus, but rather the decision of a tiny, self-selected group, a small fraction of the global astronomical community. This limited participation fueled immediate and impassioned opposition. Among the most vocal critics was Alan Stern, a leading planetary scientist and the principal investigator of the New Horizons mission, which was, even then, hurtling towards Pluto. Stern immediately decried the new definition as unscientific and unworkable, a compromise that created more problems than it solved. He famously coined the term dwarf planet, not as a new category, but as a pejorative, a demeaning label for worlds he believed were every bit as deserving of full planetary status. This wasn't merely a semantic squabble. It was a philosophical wound that deeply divided the scientific community, leaving many feeling that a flawed, sociological process had overshadowed pure scientific inquiry. It was a decision that, in its very making, set the stage for a spectacular and profoundly ironic rebuttal from Pluto itself. On the 15th of July, 2015, after a journey spanning 9 years and 5 billion kilometers across the vast, frozen expanse of our solar system, a small, intrepid spacecraft known as New Horizons broadcast a message that would fundamentally redefine our understanding of distant worlds. This was no ordinary transmission. It was, in essence, Pluto's grand rebuttal, a defiant postcard sent from the very edge of our cosmic neighborhood, transforming our perception of what a small, cold body could truly be. For decades, Pluto had languished in the public and scientific imagination as little more than a simple, inert, cratered ice ball, a static relic of the early solar system, perpetually frozen and unchanging. Yet, the high-resolution images and sophisticated instruments aboard the New Horizons probe revealed a stunningly complex reality, a world teeming with unexpected signs of recent and ongoing geological activity, a phoenix-like rebirth for a celestial body so recently stripped of its full planetary status. One of the most breathtaking revelations emerged from Sputnik Planitia, a vast, heart-shaped basin of nitrogen ice that dominates Pluto's northern hemisphere. This colossal feature, roughly 1,000 kilometers wide, spanning an area comparable to the nation of France or the state of Texas, is far from static. Instead, it behaves like a gigantic lava lamp, its nitrogen ice in a state of slow, convective motion, churning and reshaping the surface over cosmic timescales. Scientific analysis of its almost pristine appearance indicates that this remarkable terrain is less than 10 million years old, a mere blink of an eye in the 4.5 billion year history of our solar system, proving that Pluto is geologically alive. The smooth, unblemished surface of Sputnik Planitia suggests active processes are constantly resurfacing the basin, erasing craters almost as quickly as they form. Beyond the icy heartland, the New Horizons mission unveiled towering mountains of water ice, rising several kilometers from Pluto's surface. Structures like Wright Mons, which stands approximately 4 kilometers tall and extends for 150 kilometers across, are strong candidates for being massive cryovolcanoes. These aren't volcanoes erupting molten rock, but rather colossal geological features that would have spewed slushy, icy mixtures of water, ammonia, and methane from Pluto's interior onto its frigid surface. The very existence of such geological engines on a world so far from the Sun, where internal heat was previously thought to be minimal, challenges long-held assumptions about where planetary activity can occur. It suggests a surprising reservoir of internal energy, perhaps sustained by radioactive decay within Pluto's core. As New Horizons swept past, it also analyzed Pluto's atmosphere, revealing a complex, multi-layered blue haze far more extensive than any scientists had predicted. This nitrogen-rich atmosphere, though tenuous, extends for hundreds of kilometers above the surface, interacting with solar ultraviolet light. This interaction gives rise to intricate patterns of tholins, reddish organic compounds that rain down onto Pluto's surface, creating its distinctive ruddy hue. The presence of these complex organic molecules, born from the interplay of sunlight and methane in the atmosphere, hints at a surprisingly dynamic and complex chemistry on this distant world, opening new avenues for astrobiological speculation. From a geological perspective, the sheer volume of New Horizons data effectively rendered the International Astronomical Union's classification debate moot. Regardless of what its orbital neighbors were doing, or whether it had cleared its neighborhood, Pluto demonstrated all the complexity, dynamism, and internal processes of a real planet. The mission, perhaps with a touch of cosmic irony, was led by the very same Alan Stern who had so vehemently opposed Pluto's demotion back in 2006. For Stern and his team, the stunning revelations from New Horizons felt like a triumphant vindication, a powerful statement from a world long underestimated. The irony was palpable. A world demoted for not being gravitationally dominant was revealed to be internally, geologically, and atmospherically dominant and vibrantly alive. This postcard from the Edge didn't just give us a picture of Pluto, it gave us a picture of a new type of world, one that vigorously challenges our deeply ingrained, sun-centric ideas about the very nature of planetary activity in the universe. Have you ever considered that losing something, even a concept as fundamental as the definition of a planet, can actually lead to an extraordinary gain? The story of Pluto, a narrative that has spanned nearly a century of human endeavor and scientific discovery, does not merely conclude with a reclassification or the breathtaking imagery from a distant spacecraft. Instead, it culminates in a profound expansion of our cosmic perspective, a testament to how humility in the face of new data can unlock an entire empire of diverse and fascinating new worlds, reshaping our very understanding of the universe we inhabit. For generations, our solar system was depicted as a neat, almost simplistic collection of 8, then 9, planets orbiting our Sun, with some leftover debris scattered in between. But the ultimate lesson gleaned from the Pluto saga reveals a far richer, more layered ecosystem, a celestial tapestry woven with distinct populations of objects, each playing a vital role. Beyond the familiar gas giants, extending billions of kilometers into the frigid darkness, lies the Kuiper Belt, a vast, unexplored third continent of our solar system, brimming with icy denizens that challenge our preconceptions of what a world can be. Within this expansive icy domain, the term dwarf planet, once seen by many as a consolation prize or a pejorative label, is now being re-evaluated. It is, in fact, the proper nomenclature for the majestic kings and queens of this distant, frigid realm. These dwarf planets, objects like Pluto, Eris, Haumea, and Makemake, are not mere cosmic pebbles. They represent a class of planet-like objects that may well be the most common type of world throughout our Milky Way galaxy, far outnumbering the terrestrial or gas giant planets. To understand our cosmic neighborhood, we must recognize the true significance of these icy monarchs. Perhaps one of the most compelling implications stemming from Pluto's journey, especially after the revelations of New Horizons, is its profound connection to the broader search for life beyond Earth. The irrefutable evidence of ongoing geological activity on Pluto, with its vast nitrogen glaciers that are less than 10 million years old, and the strong indications of massive cryovolcanoes like Wright Mons, which may erupt icy mixtures from within, radically expands our concept of potentially habitable zones in planetary systems. It forces us to ask, could life thrive far from the warmth of its star? Consider the implications if a small world, one residing at an average distance of nearly 6 billion kilometers from the Sun, can retain enough internal heat from the slow, steady decay of radioactive elements within its core to power geology and sustain liquid water beneath its frozen surface. This changes everything we thought we knew about the conditions necessary for life. It suggests that the traditional, narrow, sun-warmed orbits we have traditionally focused on in our search for extraterrestrial biology might be just one small part of a much larger, more diverse cosmic tapestry of potential abodes for life. The universe, it seems, is far more forgiving than we once dared to imagine. The classification debate that once raged in the halls of the International Astronomical Union, while contentious, has ultimately led us to a more nuanced understanding of scientific categorization itself. It has taught us that science often requires multiple definitions for a single word, especially one as loaded and historically charged as planet. For astronomers who meticulously chart orbits and gravitational interactions, a dynamical definition focused on orbital dominance remains crucial. Yet, for geologists and planetary scientists who delve into the intrinsic properties of worlds, their internal heat, their geological processes, their atmospheric compositions, a geophysical definition centered on an object's inherent characteristics is equally vital. Pluto's story teaches us that scientific progress is rarely about simplifying. It is about replacing simple, elegant categories with more complex, nuanced, and ultimately far more accurate descriptions of reality. This entire saga, from a mistaken giant to a demoted planet to a surprisingly active ice world, serves as a powerful metaphor for the scientific process itself. It is a continuous journey of correcting our mistakes, of embracing the inherent complexity of the cosmos, and of constantly expanding our definition of what is truly possible in the universe. In the end, Pluto's reclassification was not a loss. It was a profound promotion for our understanding, proving beyond a doubt that sometimes a demotion can be the most powerful, most enlightening promotion of all, opening our eyes to an entire new frontier in the ongoing quest to comprehend our magnificent cosmos.